This is investigation 2 of the Working Energy Lab. I've already done this because this is another one of those things that takes several tries to get it right because it depends on my coordination. What I did is I took a 200-gram mass, as it says in the lab manual, hung it from the force probe, held it over the motion detector, and then lifted it at a constant speed. That was the tricky part. I got something that looks pretty good, and I'm going to show it to you in close-up now. The top graph with the red line is the force. The middle graph, this one, is the position. And the bottom line is the velocity. And that's probably as good a constant velocity as I can get. So we're going to look at the time interval from 1 second to 2 seconds. All right. Your manual says for you to sketch the velocity and the force graphs. The scale on the graphs in the manual, you're going to need to change because we did not go to 10 seconds. We gathered data for 3 seconds, and you can see over here, I was reaching the limit of how high my hand would go, and that's why that looks a little bit spiky. So the average value for the force is 2.284 newtons. 2.284 newtons. The starting position was 0.2522 meters. The ending position was 0.4983 meters. So 0.4983 minus 0.2522 meters is your distance, and your force was 2.284 newtons. Now, investigation 2.2 says to change the force time graph axes to force position. I'm going to do that now. Just come over here to time, click, go to position. We need to auto scale that again. And I need to start from point 252. It's not going to be exact. Go to 0.498. What we're going to do here is we are going to calculate the area under the curve using this feature. The result is that the area under the curve is 0.5395 Newton meters. You will recall from lecture that Newton meters are units of energy known as joules. That is the work done by the force lifting the hanging mass. So when I lifted that over this distance, I did 0.5395 joules of work. That concludes this video.